2.47 million years ago, something passed through our solar system. It was not an asteroid, it was not a comet, it was not a rogue planet or a cloud of interstellar dust. It was an entire star, a sun roughly the same size as our own, drifting silently through the darkness, pulled by nothing more than the slow currents of galactic gravity. And it came so close that it may have carved a path straight through the vast cloud of frozen bodies that surrounds our planetary neighborhood. No one saw it, no one could have. The earliest ancestors of our species were only just beginning to walk upright on the plains of East Africa. They had no telescopes, they had no written language, they had no understanding of what a star even was, let alone the knowledge that one could wander so close to home. And yet, this silent visitor may have set in motion a chain of events that shaped the very world they would inherit. The star is called HD 7977. It is a G-type main sequence star, which means it is almost identical to our Sun in mass and temperature. Right now, it sits roughly 247 light-years away in the constellation Cassiopeia, an unremarkable point of light among billions. You cannot see it with the naked eye. You would need a reasonably powerful telescope to pick it out from the crowded star fields of the northern sky. But rewind the clock 2.5 million years, and HD 7977 was not far away at all. It was here. According to calculations based on data from the European Space Agency's Gaia spacecraft, HD 7977 may have passed as close as to 2,300 astronomical units from our Sun. To put that in perspective, the nearest star to us today, Proxima Centauri, is roughly 270,000 astronomical units away. HD 7977 came more than 100 times closer than any star near us now. It did not merely pass by our solar system. It walked through the front door, and here is where the story takes a darker turn. Our solar system is not simply a collection of 8 planets orbiting a star. It is surrounded by an enormous shell of icy debris, known as the Oort Cloud, a sphere of trillions of frozen objects, stretching out to distances of 100,000 astronomical units or more. These are the remnants of the solar system's formation, ancient chunks of ice and dust and rock that never coalesced into planets. They drift in near-perfect stillness, held loosely by the sun's gravity, at the very edge of its gravitational influence. When a star passes through this region, it acts like a hand sweeping through a pool of still water. It stirs things up. It pushes objects out of their ancient orbits. Some are flung into interstellar space, lost forever. Others are nudged inward, toward the sun, toward the inner solar system, toward Earth. The result is something astronomers call a comet shower. And a comet shower aimed at the inner solar system is one of the most dangerous events that can occur in the life of a planetary system. A team of researchers led by Zoya Tao and Abraham Loeb at Harvard published a study in 2025 suggesting that the passage of HD 7977 may have triggered exactly this kind of event. Their simulations showed that, depending on the star's closest approach distance, anywhere from 2,300 to 13,000 astronomical units, the probability of kilometer-sized comets striking Earth increased by an order of magnitude compared to normal background rates. The expected number of such impacts over the duration of the shower was roughly 5, and the timing of this enhanced bombardment aligns with one of the most significant transitions in Earth's geological history. The shift from the Pliocene to the Pleistocene epoch, the very moment when our planet tipped into the cycle of ice ages that would define the next 2.5 million years. A star no one noticed may have rewritten our planet's future. By the end of tonight, you're going to understand how a single stellar flyby, lasting only a few thousand years, could disturb billions of frozen objects in the outer solar system, send a rain of comets cascading toward the inner planets, and possibly contribute to the dramatic climatic shift that transformed Earth into the world we know today. You will learn what the Oort Cloud is, why it matters, and why it remains one of the most fragile and consequential features of our solar system. You will see how scientists use spacecraft data to trace the paths of stars through deep time, and why the arrival of the Gaia mission has opened an entirely new chapter in our understanding of the dangers that lurk in our galactic neighborhood. You will encounter other stars that have visited us in the past, and others that are on their way, and you will come to understand that the solar system is not the stable, self-contained mechanism that we were taught in school. It is an open system, subject to forces that originate far beyond the orbit of the outermost planet, forces that operate on timescales that make all of human civilization seem like a single heartbeat. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. To understand what HD 7977 did when it passed through our solar system, we first need to understand what our solar system actually looks like. Not the simplified diagram from a textbook, with 8 neat circles around a yellow dot. The real thing, the sprawling, layered, almost incomprehensibly vast structure that extends far beyond the orbit of the outermost planet and deep into the surrounding interstellar space. Start with what you know. Earth orbits the Sun at an average distance of about 149.6 million kilometers. Astronomers call this distance 1 astronomical unit, abbreviated AU. It takes light roughly 8 minutes and 20 seconds to cross it. This is the fundamental yardstick of planetary science, the unit against which all other distances in the solar system are measured. Mercury, the closest planet to the Sun, orbits at about 0.4 astronomical units. Mars sits at about 1.5. Jupiter, the giant, orbits at 5.2. Saturn at 9.5. Uranus at 19.2. And Neptune, the farthest recognized planet, orbits at roughly 30 astronomical units from the Sun. If you were to shrink the Sun down to the size of a basketball, about 24 centimeters in diameter, then Earth would be a small peppercorn roughly 26 meters away. Jupiter would be a marble about 135 meters away. Neptune would sit nearly 800 meters from the basketball. That is already a considerable stretch of space. You would need a good pair of binoculars to see the basketball from Neptune's position. But the solar system does not end at Neptune, not even close. Beyond Neptune lies the Kuiper Belt, a ring of icy bodies and dwarf planets that includes Pluto, Eris, Makemake, and Haumea, among thousands of other objects. The Kuiper Belt extends from roughly 30 to about 55 astronomical units from the Sun. It is a broad, flat ring of debris, similar in some ways to the asteroid belt between Mars and Jupiter, but far more massive and far more spread out. The total mass of the Kuiper Belt is estimated at roughly 10% of Earth's mass, though this figure is uncertain. In our basketball model, the Kuiper Belt would stretch from about 800 meters to roughly 1.5 miles from the center. Significant, certainly, but still just the innermost fringe of the solar system's true extent. Because beyond the Kuiper Belt, there is something much larger, something that dwarfs everything we have discussed so far by orders of magnitude: the Oort Cloud. The Oort Cloud is a theoretical sphere of icy bodies that envelops the entire solar system. Its inner edge begins somewhere around 2,000 to 5,000 astronomical units from the Sun, depending on the model. Its outer edge extends to roughly 100,000 astronomical units, perhaps even 200,000. In our basketball model, where the Sun is a ball you can hold in your hands and Earth is a peppercorn 26 meters away, the inner edge of the Oort Cloud would begin approximately 55 kilometers from the basketball. Its outer boundary would lie more than 2,700 kilometers away. That is roughly the distance from New York City to Denver, Colorado, or the distance from London to Istanbul. The solar system, in its full extent, is not a neighborhood, it is not a city, it is a continent, and the Oort Cloud is by far its largest feature, accounting for more than 99.9% of the solar system's volume. Here is another way to grasp the scale. If the entire solar system, from the Sun to the outer edge of the Oort Cloud, were compressed to the length of a football field, 100 yards, then the orbit of Neptune would occupy only the first 3/100ths of an inch, less than a millimeter. The Kuiper Belt would end before you had moved the width of a pencil lead from the goal line. Everything you have ever learned about the solar system, all 8 planets, all the moons, all the asteroids, all the missions, all the drama, all of it happens within the first imperceptible sliver of the field. The remaining 99.9 yards belong to the Oort Cloud, empty, dark, silent, and filled with trillions of frozen objects that most people have never heard of. No one has ever directly observed the Oort Cloud, No telescope has ever captured an image of it. No spacecraft has ever reached it. Voyager 1, the most distant human-made object ever created, was launched in September of 1977. As of now, it is rough 163 astronomical units from the Sun, traveling at about 17 kilometers per second. At that speed, it will not reach the inner edge of the Oort cloud for another 300 years. It will not exit through the outer edge for roughly 30,000 years. Even our fastest spacecraft, moving at speeds that would carry you from New York to Los Angeles in 5 minutes, will spend thousands of years crossing a region of space that we have never directly sampled. The Oort cloud is so far away, so diffuse, and so dark that we know it exists only through indirect evidence. The primary evidence comes from the orbits of long-period comets. Long-period comets are comets with orbital periods greater than 200 years. Some have periods of thousands or even millions of years. They arrive from all directions in the sky, not just from the flat plane where the planets orbit. Some come from above the ecliptic, some from below, some from the direction of the galactic center, some from the opposite direction. This isotropy, this coming from everywhere quality, tells astronomers that their source must be spherical, surrounding the solar system on all sides, rather than confined to a flat disk like the Kuiper belt. In 1950, the Dutch astronomer Jan Hendrik Oort analyzed the orbits of 19 long-period comets and noticed something remarkable. When he traced their orbits backward to determine their original distances from the Sun before they were perturbed into the inner solar system, he found that most of them originated at distances of roughly 20,000 to 50,000 astronomical units. This clustering suggested the existence of a vast reservoir of icy bodies at the far edge of the Sun's gravitational domain. Oort proposed that this reservoir was continuously being depleted by gravitational perturbations from passing stars and the galactic tide, sending a slow but steady stream of comets into the inner solar system. The cloud that bears his name has been a cornerstone of planetary science ever since, even though, 76 years later, it has never been directly observed. Current estimates suggest that the Oort cloud contains somewhere between several hundred billion and 2 trillion objects larger than 1 kilometer in diameter. Some models push the total number of objects of all sizes into the tens of trillions. The combined mass of the Oort cloud is thought to be roughly 5 to 100 Earth masses, though these figures remain deeply uncertain. Much of this uncertainty stems from the fact that we can only observe Oort cloud objects when they happen to fall into the inner solar system and become visible as comets. The vast majority of Oort cloud bodies never come close enough to the Sun to be detected. They remain in the outer darkness, invisible and uncountable. What is certain is that the objects within the Oort cloud are not tightly bound to the Sun. They orbit at such vast distances that the Sun's gravitational pull on them is extremely weak. At 100,000 astronomical units, the Sun's gravitational acceleration is roughly 1/10 billionth of what it is at Earth's distance. An object at the outer edge of the Oort cloud moves at a speed of only a few meters per second relative to the Sun, taking tens of millions of years to complete a single orbit. These objects are barely held in place. A slight nudge, a gentle gravitational tug from a passing object, can be enough to alter their trajectories dramatically. This is where the danger lies. And to understand just how precarious the situation is, we need another scaled comparison. If the Sun's gravity were a radio signal broadcast from a tower, its strength at 1 astronomical unit at Earth's distance would be overwhelming. You would be standing directly beside the transmitter. At Neptune's distance, 30 astronomical units out, the signal would have faded considerably, reduced to about 1/900th of its original strength, but it would still be clearly detectable. You could tune in without difficulty. At the inner edge of the Oort cloud, 2,000 astronomical units away, the signal would be a whisper, reduced by a factor of 4 million. You would need highly sensitive equipment to pick it up at all. At the outer edge, 100,000 astronomical units, the signal would be reduced by a factor of 10 billion. It would be indistinguishable from background noise. The objects at the outer edge of the Oort cloud are like boats drifting on a calm sea, held in place by the faintest current. The slightest breeze can push them off course, and the breezes are constant. The Oort cloud is continuously shaped by two forces operating on different timescales. The first is the galactic tide, the combined gravitational influence of all the matter in the Milky Way, including its disk of stars and gas, its central bulge, and its massive halo of dark matter. The galactic tide is slow and gentle, operating over millions of years, but it is relentless. It gradually torques the orbits of Oort cloud objects, changing their inclinations and eccentricities, and occasionally sending some of them drifting inward toward the Sun on timescales of millions of years. The galactic tide is responsible for most of the long-period comets that we observe, arriving in the inner solar system during quiet periods, when no stellar encounter has recently stirred the cloud. The second force is stellar encounters. Stars in the Milky Way are not stationary. They orbit the galactic center at various speeds and inclinations, and their paths weave among one another like threads in an enormous tapestry. When a star passes close to the solar system, its gravity adds an additional perturbation on top of the galactic tide. The strength of this perturbation depends on the mass of the star, its closest approach distance, and its velocity relative to the Sun. A massive, slow-moving star passing close by produces a much stronger perturbation than a small, fast-moving star passing at a greater distance. On average, a star passes within 1 parsec, roughly 3.26 light-years, or about 206,000 astronomical units, of the Sun approximately once every 100,000 years. A star passing within the outer Oort cloud itself, within 100,000 astronomical units, happens perhaps once every 100,000 to 500,000 years. A star penetrating deep into the inner Oort cloud within 20,000 astronomical units, where the density of cometary objects is thought to be highest, is considerably rarer, occurring perhaps once every few million years. And a star coming within a few thousand astronomical units of the Sun, as HD 7977 may have done, is an event that occurs perhaps once every several tens of millions of years. The origin of the Oort cloud itself is a story of violence and chaos. During the first few 100 million years of the solar system's existence, the giant planets were not in their current positions. According to the Nice model, named after the city in France where it was developed, the giant planets formed in a more compact configuration and then migrated outward over a period of several 100 million years. This migration was driven by gravitational interactions with a massive disk of small icy bodies, the remnants of planet formation, that surrounded the Sun beyond the orbit of the outermost giant. As the planets migrated, they scattered this disk in all directions. Many objects were flung inward, bombarding the inner planets in the late heavy bombardment that scarred the surfaces of the Moon, Mercury, and Mars with the craters we see today. Others were flung outward, on trajectories that carried them to enormous distances from the Sun. Those that were flung with just enough velocity to escape the immediate gravitational influence of the planets, but not enough to leave the Sun's gravitational sphere of influence, entirely settled into the distant, weakly bound orbits that form the Oort cloud. Some models suggest that the Sun's birth cluster also contributed to the Oort cloud's formation. The Sun, like most stars, formed in a cluster of hundreds or thousands of stars. Within this cluster, stars were much closer together than they are in the current solar neighborhood, and gravitational interactions between cluster members were frequent. These interactions could have scattered icy bodies from the protoplanetary disks of neighboring stars into the Sun's gravitational domain, contributing additional material to the Oort cloud. In this scenario, a significant fraction of the Oort cloud's population may not even be native to our solar system. It may have been stolen from the debris disks of other stars during the first few million years of the cluster's existence, before the cluster dispersed and its members drifted apart. This means that the Oort cloud is not merely a relic of our solar system's formation. It is potentially a composite structure, assembled from material originating in multiple star systems, each contributing its own unique mix of ices, dust, and organic compounds. When a comet from the Oort cloud falls into the inner solar system and is observed by astronomers, it may be carrying a chemical record not just of our own protoplanetary disk, but of the disks of long-lost sibling stars, systems that formed alongside ours and then went their separate ways billions of years ago. This connection to other stars adds yet another layer to the significance of the Oort Cloud. It is not just a boundary between our solar system and the galaxy. It is a shared inheritance, a commons where the debris of multiple star systems mingles and drifts in the gravitational twilight between worlds. The European Space Agency's Gaia spacecraft has transformed our ability to track these encounters. Gaia was launched in December of 2013 from the Guiana Space Center in Kourou, French Guiana. Its mission is to create the most detailed three-dimensional map of the Milky Way ever produced, measuring the positions, distances, and motions of stars across the galaxy with extraordinary precision. Gaia observes from a vantage point at the Sun-Earth Lagrange Point 2, about 1.5 million kilometers from Earth in the direction opposite the Sun, where it slowly rotates, scanning the entire sky repeatedly over the course of its mission. Gaia's first major data release came in September of 2016. The second release, in April of 2018, provided positions and proper motions for over 1.3 billion stars, along with radial velocities for roughly 7.2 million of them. The third release, in June of 2022, expanded the catalogue to nearly 2 billion sources with improved precision. This wealth of data allows researchers to trace the trajectories of nearby stars backward and forward in time with this unprecedented accuracy. The astronomer Corinne Baylor-Jones, working at the Max Planck Institute for Astronomy in Heidelberg, Germany, was among the first to use Gaia data systematically to catalogue stellar encounters. In a landmark 2018 paper, Baylor-Jones and his team identified dozens of stars that have passed or will pass within 2 parsecs of the Sun over the past and next 10 million years. They used a combination of Gaia positions, proper motions, parallaxes, and radial velocities, integrated through a model of the Milky Way's gravitational potential to reconstruct stellar trajectories. Among these encounters, HD 7977 stood out. Using Gaia data combined with earlier observations from the Hipparcos satellite, which operated from 1989 to 1993, Baylor-Jones calculated that HD 7977 passed the Sun with a median perihelion distance of about 0.43 parsecs, roughly 1.4 light-years, approximately 2.8 million years ago. That alone made it a noteworthy encounter, close enough to enter the outer reaches of the Oort Cloud. But subsequent analyses told a more alarming story. Polish astronomers Piotr Dybczynski and Małgorzata Królikowska, working at Adam Mickiewicz University in Poznan, refined the trajectory of HD 7977 using Gaia Early Data Release 3. Their results were startling. They found that HD 7977 may have passed as close as 0.015 parsecs from the Sun, roughly 3,100 astronomical units. That would place the star well inside the inner Oort cloud, the densest, most consequential part of the entire structure. At that distance, the gravitational influence of a solar mass star would be enormous. It would not just nudge a few comets. It could reshape the entire inner cloud. There is an important caveat. HD 7977 has a renormalized unit weight error, known as ROBWE, of approximately 2.015 in the Gaia Data Release 3 catalogue. A ROBWE value significantly above 1.0 suggests that the star's measured position may be unreliable. The most likely explanation is that HD 7977 is an unresolved binary system, 2 stars orbiting each other so closely that Gaia cannot distinguish them individually. If this is the case, then the calculated proper motion is contaminated by the orbital wobble of the binary components, and the inferred trajectory could be significantly wrong. The closest approach distance might have been 3,000 astronomical units, or it might have been 30,000 astronomical units. The difference between these two numbers is the difference between a catastrophe and a footnote. Future Gaia data releases, particularly the final catalogue expected in the late 2020s, are anticipated to resolve this question by including dedicated solutions for binary star systems. Until then, HD 7977 remains a star of immense interest and immense uncertainty. But even the conservative estimates place it among the closest known stellar flybys in the past several million years, and the closer it actually came, the more profound its effects would have been. What happened when this star encountered the Oort Cloud is a question that leads us into some of the most consequential physics in planetary science. And the answer begins with a force so subtle that you cannot feel it, so gentle that it takes millions of years to act, yet so powerful that it can redirect the trajectory of a frozen body across billions of kilometers of space. That force is gravity, and when wielded by a passing star, it becomes a weapon of mass disruption. But before we confront that force, it is worth lingering on the instrument that made this discovery possible. The Gaia spacecraft itself is a marvel of precision engineering. It carries two telescopes, separated by a fixed angle of 106.5 degrees, that feed light onto a single focal plane containing over 1 billion pixels, the largest digital camera ever flown in space. As the spacecraft slowly rotates, completing one full revolution every 6 hours, the two telescopes sweep across different parts of the sky, measuring the positions of stars as they pass through the field of view. Over the course of its mission, each star is observed dozens to hundreds of times, and the accumulation of these repeated measurements allows Gaia to determine positions, proper motions, and parallaxes with astonishing precision. The parallax measurement is particularly important for the story of HD 7977. Parallax is the apparent shift in a star's position on the sky, caused by Earth's orbital motion around the Sun. By measuring this shift with extreme precision, Gaia can determine the distance to each star. For HD 7977, Gaia measured a parallax that places the star at approximately 75 parsecs, or about 247 light-years from the Sun, combined with the proper motion and radial velocity. This distance measurement allows astronomers to calculate the star's three-dimensional trajectory through the galaxy. The challenge, as we have discussed, is that the RUWE value suggests the parallax and proper motion measurements for this particular star may be less reliable than usual. What is often overlooked in discussions of stellar flybys is the sheer computational challenge of tracing trajectories through galactic time. The galaxy is not a simple system. It contains roughly 200 to 400 billion stars, trillions of solar masses of dark matter, vast clouds of gas and dust, and a supermassive black hole at its center, weighing approximately 4 million solar masses. All of these contribute to the gravitational field through which stars move. To trace a star's trajectory accurately over millions of years, you need a model of this gravitational field that accounts for the distribution of mass throughout the galaxy. Small errors in the galactic potential model can accumulate over long integration times, adding yet another source of uncertainty to the flyby calculations. Baylor-Jones addressed this challenge by using a smooth, analytic model of the Milky Way's gravitational potential, including contributions from the disk, the bulge, and the dark matter halo. This model captures the large-scale structure of the galaxy, but does not include the effects of individual stars or molecular clouds that the Sun and HD 7977 might have passed near during the intervening 2.5 million years. These local perturbations are generally small compared to the smooth potential, but over millions of years, they can introduce additional uncertainty into the trajectory calculations. It is a reminder that even our best methods are approximations, constrained by the limits of what we can measure and model. Despite all these challenges, the convergence of evidence from multiple research groups using different methods and different data releases points to the same broad conclusion. HD 7977 passed unusually close to the Sun, approximately 2 to 3 million years ago. Whether that distance was 3,000 astronomical units or 30,000 remains to be settled, but the encounter itself is not in serious doubt. The star was here. The question is what it did while it was passing through. The fundamental problem with a stellar flyby through the Oort Cloud is not the star itself. A star passing through the solar system does not collide with anything. The spaces between objects, even in the relatively dense inner Oort cloud, are so vast that a star could pass through 1 trillion times without striking a single body. The star does not emit deadly radiation in the direction of the planets. It does not heat the Oort cloud or melt its icy inhabitants. It does not directly threaten Earth or any of the inner worlds. The problem is gravity. And gravity, unlike a bullet or a blast wave, does not need to touch you to change your life. It acts at a distance, silently, invisibly, and with absolute mathematical precision. When a star with a mass comparable to the Sun passes through the Oort Cloud, it creates a gravitational disturbance that propagates outward from its trajectory, like a wake behind a ship moving through calm water. Every object within a certain radius of the star's path feels a tug. The strength of that tug depends on three factors: the mass of the passing star, the velocity at which it moves relative to the Sun, and the distance between the star and each individual Oort cloud object at the moment of closest approach. Consider a single comet nucleus drifting at 50,000 astronomical units from the Sun. It has been there for billions of years, placed in its current orbit during the chaotic early history of the solar system, when the giant planets migrated and flung vast quantities of icy material outward. It orbits the Sun so slowly that it completes one full revolution every several million years. Its velocity relative to the Sun is perhaps a few tens of meters per second, roughly the speed of a brisk jog. For all practical purposes, it is stationary, a frozen sentinel hanging in the void, untouched since before the first complex life appeared on Earth. Now a star with the mass of the Sun approaches. It is moving at a relative velocity of perhaps 20 to 40 kilometers per second, a typical speed for stars in the solar neighborhood. It passes within a few thousand astronomical units of this comet, and for a period of perhaps a few hundred to a few thousand years, the gravitational pull of the intruding star competes with the gravitational pull of the distant Sun. The comet feels both forces simultaneously, and its response depends on the geometry of the encounter, the relative positions and velocities of all three bodies: comet, Sun, and intruder. The gravitational tug of the passing star, even at a distance of several thousand astronomical units, is enough to change the comet's velocity by a small but significant amount, perhaps a few meters per second, perhaps a few tens of meters per second. This may seem trivial, comparable to the speed at which you might push a shopping cart across a parking lot. It is not trivial at all. In the context of the Oort cloud, where orbital velocities are measured in single-digit meters per second, a change of even 1 meter per second can be transformative. A change of a few meters per second in the velocity of an Oort cloud object can alter its orbital parameters enormously. The orbit might become more eccentric, meaning its closest approach to the Sun, its perihelion, drops dramatically, while its farthest point, its aphelion, extends even farther into space. An object that previously never came closer than 40,000 astronomical units to the Sun might, after the perturbation, have a perihelion of just a few astronomical units, bringing it into the inner solar system, into the realm of the rocky planets, into the region where it can cross Earth's orbit. Alternatively, the perturbation might tilt the orbit, rotating its orientation in space. Or it might add enough energy to unbind the object from the Sun entirely, sending it flying out of the solar system and into interstellar space, never to return. For some fraction of the perturbed objects, the change in velocity is just right, in just the right direction, to send them inward. These objects become long-period comets, and some of them will, over the course of their long journeys toward the Sun, cross the orbit of Earth. This is the mechanism behind what astronomers call a comet shower, not a steady drizzle of 1 or 2 comets per decade, which is the normal rate at which Oort cloud objects drift inward due to the galactic tide and random distant stellar encounters. A comet shower is a sudden and sustained spike in the number of comets entering the inner solar system, triggered by a specific identifiable perturbation event, a passing star, a close encounter, a gravitational shove delivered to millions or billions of icy bodies simultaneously. The shower does not arrive all at once. This is a crucial point that distinguishes a comet shower from a single catastrophic impact. The perturbed comets are on orbits with periods of millions of years. They are scattered across a vast range of distances and inclinations. They do not all begin their inward journey at the same time or from the same location. As a result, the enhanced flux of comets builds gradually over a period of roughly 500,000 to 1 million years after the flyby, reaches a peak that lasts perhaps another million years, and then slowly fades over the following several million years as the last of the perturbed comets complete their long, looping orbits. The entire shower episode, from first arrival to last, can span 5 to 10 million years. This means that if HD 7977 passed through the inner Oort Cloud 2.47 million years ago, the resulting comet shower would have begun arriving in the inner solar system somewhere between roughly 2 million and 1.5 million years ago. The peak of the shower would have occurred roughly 1 to 2 million years after the flyby, and some comets from that shower might still be arriving today, trickling in as the last echoes of an encounter that happened before our species existed. To understand the mechanics of this disruption more precisely, consider what happens to a single Oort Cloud comet during a close stellar flyby. The comet is orbiting the Sun on a nearly circular orbit at, say, 10,000 astronomical units. Its orbital velocity is roughly 300 meters per second, incredibly slow by any terrestrial standard, about the speed of a fast walk. Its orbital period is approximately 30 million years. It has been in this orbit since the solar system was young. Now HD 7977 approaches. The star is moving at 25 kilometers per second relative to the Sun, roughly 83 times faster than the comet is moving in its orbit. As the star passes within a few thousand astronomical units of the comet's position, the gravitational tug changes the comet's velocity by a small amount, perhaps 5 to 10 meters per second. This change, called the velocity impulse, depends on the geometry of the encounter, including the comet's position relative to the star's trajectory, the star's mass, and its velocity. Now, 5 meters per second does not sound like much, but remember, the comet's original orbital velocity was only about 300 meters per second. A change of 5 meters per second represents roughly a 1.5% alteration in its speed. For an object on a nearly circular orbit at the edge of the Sun's gravitational influence, this is enough to change its orbital eccentricity dramatically. The orbit that was previously nearly circular, with a perihelion and aphelion both near 10,000 astronomical units, becomes highly elliptical. The aphelion might increase to 20,000 astronomical units or more, and crucially, the perihelion might drop to just a few astronomical units, bringing the comet into the inner solar system for the first time in its 4.5 billion year existence. The probability of this happening to any individual comet is small. Most Oort Cloud objects that are perturbed by a passing star have their orbits altered in ways that do not bring them close to the Sun. Their orbits become more eccentric, but their perihelia remain at thousands or tens of thousands of astronomical units. They are disturbed, but not redirected. The comets that do fall into the inner solar system represent a tiny fraction of the total number perturbed, perhaps 1 in 1,000 or 1 in 10,000, depending on the geometry and intensity of the encounter. But the total number of perturbed objects is in the billions or tens of billions. Even a fraction of 1% yields millions of objects newly directed toward the inner solar system. And it is from this vast pool of redirected comets that the shower is fed, one comet at a time, arriving over a period of millions of years, each one a messenger from an encounter that the Earth below has long since forgotten. There is one more factor that amplifies the danger. Comets are not like asteroids. They are made primarily of volatile ices, water ice, carbon dioxide, carbon monoxide, methane, and ammonia, mixed with silicate dust and organic compounds. When a comet approaches the Sun, the ices sublimate, releasing gas and dust that form the familiar coma and tail. This outgassing also acts as a rocket engine, producing non-gravitational forces that alter the comet's trajectory in ways that are difficult to predict. A comet that appears to be on a harmless trajectory can be nudged by outgassing forces onto a collision course with a planet. Conversely, a comet that appears threatening can be deflected away. This unpredictability makes long-period comets more difficult to track and more difficult to defend against than asteroids, which follow purely gravitational orbits that can be predicted with high accuracy. Furthermore, comets from the Oort Cloud are typically on their first passage through the inner solar system. They have never been heated before, never been partially depleted of their volatile content. They arrive pristine, fully loaded with ices that sublimate violently when exposed to solar heating for the first time. This makes them particularly active, producing large, bright comae and tails, but also making their orbits more subject to non-gravitational perturbations. A first-time visitor from the Oort Cloud is the most unpredictable and potentially the most dangerous type of small body that the inner solar system encounters. The study by Joya Tsao, Abraham Loeb, and Morgan McLeod at the Harvard-Smithsonian Center for Astrophysics quantified this effect using detailed numerical simulations. They modeled the Oort Cloud as a population of small bodies distributed between roughly 3,000 and 100,000 astronomical units from the Sun, with a concentration in the inner cloud between 3,000 and 20,000 astronomical units. The inner cloud was populated, according to models developed by David Vokokroliki and others, which suggest that the inclination distribution of inner Oort cloud objects may be concentrated near the ecliptic plane rather than being isotropically distributed. This assumption matters because the geometry of the stellar flyby, relative to the cloud structure, affects how many objects are perturbed. They then simulated the passage of HD 7977 through this cloud at various closest approach distances, or impact parameters, ranging from 2,300 to 13,000 astronomical units. The star's mass was set at approximately 1 solar mass, and its relative velocity was consistent with the values derived from Gaia measurements, roughly 20 to 30 kilometers per second. The results were alarming. For the closest possible flyby distance of approximately 2,300 astronomical units, the perturbations to the inner Oort cloud were massive. A significant fraction of inner cloud objects experienced changes in their orbital parameters large enough to redirect them toward the Sun. Many had their perihelia reduced below 50 astronomical units, meaning they would enter the region of the giant planets, Jupiter, Saturn, Uranus, and Neptune. A subset of those had perihelia reduced below 5 astronomical units, meaning they would enter the terrestrial planet zone, crossing the orbits of Mars, Earth, Venus, and Mercury. The simulations showed that for comets with diameters of 1 kilometer, the probability of at least one impacting Earth increased by roughly an order of magnitude compared to the steady-state background rate. For the closest flyby distance, the expected number of 1 kilometer comets hitting Earth over the duration of the shower was approximately 5. 5 impacts spread over roughly 1 million years. That works out to an average of 1 impact every 200,000 years, compared to the background rate of perhaps 1 kilometer scale impact every few million years. The Tsao and Loeb study introduced an important threshold concept that helps quantify the danger. They defined a critical diameter called d sub 0, which represents the smallest comet size for which at least one impact on Earth is statistically expected over the course of the shower. For the closest flyby distance of approximately 2,300 astronomical units, they calculated d sub 0 to be roughly 2.25 kilometers. This means that for every comet in the Oort cloud with a diameter equal to or greater than 2.25 kilometers, the probability of at least one such object striking Earth over the duration of the shower approaches or exceeds 1. For smaller comets, the probability is lower but still elevated well above the background rate. For larger comets, multiple impacts become statistically plausible. This threshold diameter is a powerful conceptual tool. It tells you in a single number how dangerous a given flyby was. A flyby that produces a d sub 0 of 10 kilometers is relatively benign, meaning that even the largest Oort cloud objects are unlikely to hit Earth as a result of the perturbation. A flyby that produces a d sub 0 of 1 kilometer or less is catastrophic, implying that the bombardment would include numerous impacts from objects large enough to cause continental-scale devastation. HD 7977, if it came as close as the data suggest, falls into an intermediate category, dangerous enough to significantly elevate the impact risk for kilometer-scale objects, but not so close as to guarantee civilization-ending strikes. The size distribution of Oort cloud objects is not well known, which adds another layer of uncertainty. If the Oort cloud contains relatively few objects larger than a few kilometers, then even a close stellar flyby produces a manageable number of dangerous comets. If the Oort cloud is richer in large bodies than current models suggest, the consequences could be far more severe. This uncertainty is one of the fundamental limitations of the entire analysis. We are trying to assess the danger of a weapon whose ammunition we have never been able to count, and it gets worse. The threshold diameter at which the collision probability reaches unity, meaning at least one impact is virtually guaranteed over the course of the shower, was calculated to be approximately 2.25 kilometers. For the closest flyby distance, any comet from the shower, with a diameter of 2.25 kilometers or larger, was essentially certain to hit Earth at some point during the shower's duration. A cometary impactor of that size, traveling at a velocity of perhaps 50 kilometers per second, carries kinetic energy equivalent to roughly 100 million megatons of TNT. That is approximately 1 billion times the energy released by the atomic bomb dropped on Hiroshima in 1945. The impact of such an object would excavate a crater tens of kilometers wide. It would inject billions of tons of dust and debris into the atmosphere, blocking sunlight for months or years. It would trigger global wildfires, acid rain, and a prolonged impact winter that could devastate ecosystems worldwide. But here is the problem. We do not know how close HD 7977 actually came. The uncertainty in the flyby distance spans an enormous range. The star's LWEBU value of approximately 2.015 suggests that its astrometric solution may be unreliable. If HD 7977 is an unresolved binary system, then the calculated proper motion is contaminated by the orbital wobble of the two stellar components, and the inferred closest approach distance could be significantly wrong. The actual closest approach might have been 3,000 astronomical units, a devastating penetration of the inner Oort cloud, or it might have been 10,000 astronomical units, a moderately close encounter that would produce a noticeable but less intense shower, or it might have been 30,000 astronomical units, a glancing passage through the outer cloud that would leave barely a trace. At a closest approach of 13,000 astronomical units, the upper end of the range considered by Tao and colleagues, the effects on the Oort cloud are much more modest. The perturbation is weaker, the number of comets deflected inward is smaller, the resulting shower is far less intense, the probability of a kilometer-scale impact on Earth drops considerably. At 30,000 astronomical units or more, the effects become negligible. The star passes through the outer cloud, perhaps displacing a few comets, but without significantly altering the overall flux of material into the inner solar system. This range of possibilities, from devastating bombardment to minor perturbation, is what makes HD 7977 simultaneously so fascinating and so frustrating for planetary scientists. The data says the star was here. The physics says a close encounter would have produced serious consequences, but the data is not precise enough to tell us exactly how close the encounter was, and therefore how serious the consequences actually were. It is important to place the potential HD 7977 comet shower in the context of what we know about impact rates on Earth over geological time. The current baseline rate of impact events is reasonably well constrained for the past few hundred million years, thanks to the geological preservation of large impact craters on continental surfaces. For impactors larger than 1 kilometer in diameter, the estimated rate is roughly one impact every 500,000 to 1 million years. For impactors larger than 10 kilometers, the rate drops to roughly one every 100 million years. The Chicxulub impactor that ended the Cretaceous period was a roughly 10-kilometer body, and it remains the only confirmed impact of that scale in the past several hundred million years. A comet shower like the one potentially triggered by HD 7977 would elevate the impact rate above this baseline, particularly for bodies in the 1 to 5 kilometer range. The Tau and Loeb simulations suggest an enhancement factor of roughly 5 to 10 for the closest flyby distances, meaning the rate of kilometer-scale impacts could increase from 1 every million years to 1 every 100 to 200,000 years. This is a significant increase, but it is not an extinction-level bombardment. It is more like a persistent drizzle of moderately large impactors, each one individually capable of causing regional devastation widespread crop failures, and temporary climate disruption, but not necessarily global extinction. The distinction between a single giant impact and a sustained shower of moderate impacts is important for understanding the potential environmental consequences. A single 10-kilometer impactor delivers all its energy in a single catastrophic moment, producing immediate global effects including firestorms, nuclear winter conditions, and acid rain. A shower of 1-kilometer impactors delivers a similar total amount of energy, but spread over millions of years in discrete events separated by long intervals. The planet has time to recover between blows, ecosystems can rebuild, species can adapt, but if the intervals between impacts are short enough, and if the impacts coincide with other stresses such as climate change or volcanic activity, the cumulative effect could be significant. This is what makes the coincidence between the HD 7977 flyby and the Pliocene-Pleistocene transition so intriguing. The transition was not caused by a single cataclysmic event. It was a gradual shift, unfolding over hundreds of thousands of years, driven by multiple factors acting in concert. A sustained increase in cometary bombardment could have been one of those factors, providing periodic jolts to the climate system that reinforced the trends already in motion. Not the sole cause, but a contributing factor, a thumb on the scale. Now let us examine the circumstantial evidence that might help narrow the possibilities. The timing of HD 7977's flyby, approximately 2.47 million years ago, coincides with one of the most significant climatic transitions in Earth's recent geological history, the Pliocene-Pleistocene boundary. The Pliocene epoch lasted from roughly 5.3 million to 2.6 million years ago. It was a period of relative warmth compared to today. Global average temperatures were perhaps 2 to 3 degrees Celsius higher than present levels. Sea levels were an estimated 15 to 25 meters higher, due to the reduced extent of polar ice. Forests extended to latitudes that today are covered by tundra. The Antarctic ice sheet, while present, was smaller and more dynamic than it is now. North America, Europe and Asia had no permanent ice sheets. The world was a warmer, wetter, more stable place than the one we inhabit. Then, beginning around 2.7 to 2.6 million years ago, the climate shifted dramatically. Glaciation intensified in the northern hemisphere. Ice sheets expanded across Scandinavia, Greenland, and northern North America for the first time in hundreds of millions of years. Global temperatures dropped by several degrees. Ocean circulation patterns changed as ice locked up fresh water at high latitudes. The world entered the cycle of ice ages and interglacial periods, the glacial-interglacial oscillation that would define the Pleistocene epoch and ultimately shape the environment in which our species evolved. The causes of this transition are debated, and multiple factors were almost certainly at work. Changes in Earth's orbital parameters, the Milankovitch cycles, altered the distribution of solar energy across the planet's surface, promoting ice sheet growth at high latitudes. The closure of the Central American Seaway as the Isthmus of Panama rose from the sea roughly 3 to 4 million years ago changed oceanic circulation patterns, potentially enhancing the delivery of moisture to high latitudes where it could fall as snow and build into ice. Changes in atmospheric carbon dioxide levels, driven by weathering processes and biological productivity, may have pushed the climate system across a critical threshold. These explanations are well supported by geological evidence, but some researchers have noted that the onset of Northern Hemisphere glaciation was remarkably rapid, occurring over a span of a few 100,000 years, and that the forcing mechanisms alone may not fully explain the speed and severity of the transition. Something may have provided an additional push, a perturbation to the climate system that, combined with the existing trends, tipped the balance toward a dramatically colder world. Could a comet shower, triggered by the passage of HD 7977, have provided that push? The hypothesis is speculative, and the researchers who have proposed it are careful to describe it as a coincidence that warrants further investigation rather than a proven causal link. But the timing is suggestive. A series of cometary impacts over a million-year period could inject significant amounts of dust and water vapor into Earth's stratosphere, altering atmospheric chemistry and opacity. The dust would block incoming sunlight, producing short-term cooling events. Water vapor injected into the upper atmosphere could affect the radiative balance in complex ways. Individual impacts could trigger short-term climate perturbations lasting years to decades, and a series of such events could accumulate into a longer-term trend, especially if they occurred against a backdrop of already changing orbital and oceanic conditions. There is some physical evidence. Several impact structures and tektite fields have been dated to the late Pliocene and early Pleistocene. The Eltonine impact, which occurred approximately 2.5 million years ago, involved a large body striking the ocean floor in the Bellingshausen Sea, near Antarctica. The impactor left no visible crater because it struck deep water, but it deposited a distinctive layer of extraterrestrial material, including elevated concentrations of iridium and other platinum group elements, across a wide area of the southeastern Pacific Ocean floor. The timing of the Eltonine impact is close to the Pliocene-Pleistocene boundary, within a few 100,000 years. However, analysis of the Eltonine impactor's chemical composition, published by Taggel and Clays in 2004, suggested it was asteroidal rather than cometary in origin. This weakens, but does not eliminate the connection to a comet shower. An enhanced influx of comets into the inner solar system could also increase the rate of asteroidal impacts through gravitational perturbations of asteroids by the incoming comets, or there could be both cometary and asteroidal impacts occurring during the same period for unrelated reasons. Other potential impact evidence from this period is sparse. The geological record of impacts during the Pliocene is less well studied than the Cretaceous-Paleogene boundary, partly because the impacts were probably smaller, and partly because evidence erodes over time. Oceanic impacts, which statistically should be more common since the ocean covers roughly 70% of Earth's surface, leave much less permanent evidence than continental impacts. A 2-kilometer comet striking the open ocean would create a massive but transient wave, deposit a thin layer of impact debris on the seafloor, and produce a submarine crater that would be erased by seafloor, spreading within a few tens of millions of years. The absence of a clear, unambiguous impact record does not mean the shower did not happen. It means the evidence may be too subtle, too deeply buried, or too thoroughly erased for us to find it with current methods. But here is what makes this truly terrifying. We are not talking about a singular catastrophic event, like the Chicxulub impactor that wiped out the non-avian dinosaurs 66 million years ago. That was a single decisive blow, a 10-kilometer asteroid arriving at 20 kilometers per second, releasing energy equivalent to roughly 10 billion Hiroshima bombs in a single moment. The extinction followed within months to years. A comet shower is something different. It is a sustained increase in the probability of impacts over a period of 1 to 2 million years. A slow rain of icy projectiles, arriving one every few 100,000 years, each one individually capable of regional or global devastation, but spaced far enough apart that the Earth has time to partially recover between blows. It is death by 1,000 cuts, spread over 1,000,000 years. Not a single apocalypse, but a prolonged era of elevated danger, during which any given century might bring a catastrophic impact, or might pass without incident. The randomness is the cruelty. There is no way to predict when the next comet will arrive, no way to prepare for a specific date, no way to know whether the shower is still ongoing or has already ended, and the mechanism that caused it, a passing star, is not a freak occurrence. Stars pass near the solar system all the time. It has happened before. It is happening now. Schultz's star came through the outer Oort Cloud roughly 70,000 years ago, and it will happen again. Gliese 710 will enter the cloud in approximately 1.3 million years. These are not theoretical possibilities. They are measured trajectories of real stars, calculated from precise observations. To put the velocities involved in human terms, consider this. HD 7977 was moving through the solar system at roughly 20 to 30 kilometers per second relative to the Sun. That is about 72,000 to 108,000 kilometers per hour. At that speed, You could travel from Earth to the Moon in roughly 3.5 to 5 hours. You could cross the Atlantic Ocean in about 3 minutes. You could circumnavigate the Earth in slightly more than 20 seconds. And yet, even at this tremendous speed, the star spent thousands of years within the Oort Cloud. The cloud is simply that large. At 30 kilometers per second, it takes roughly 15,000 years to cross from one side of the inner Oort Cloud to the other, and roughly 160,000 years to traverse the full extent of the outer cloud. The encounter was not a momentary flash. It was a slow, grinding passage that gave gravity ample time to do its work. Something is wrong with our assumptions about the stability of the solar system. We are taught that the planets trace fixed orbits around an unchanging sun, that the solar system is a self-contained, predictable mechanism, a clockwork model that has been running in essentially the same configuration for 4.5 billion years. And in a narrow sense, this is true. The planetary orbits are remarkably stable over timescales of billions of years, as long as no external force disturbs them. But the Oort Cloud is not part of this stable inner system. It is the interface between the solar system and the galaxy, and at that interface, stability is an illusion. The Oort Cloud has been continuously shaped, stirred, and depleted by external forces throughout its entire history. It is not a fixed structure. It is a dynamic, evolving population of objects, constantly gaining and losing members, constantly responding to the gravitational environment of the galaxy. The question is not whether the Oort Cloud has been disturbed. The question is how many times, how severely, and what the consequences were each time. HD 7977 is one candidate. There are certainly others, stretching back billions of years into the deep past, long before any life existed on Earth, to witness the resulting comet showers. If a star really did plough through our Oort Cloud 2.5 million years ago, how would we prove it? How would we separate a genuine comet shower from the steady background drizzle of long-period comets that arrives regardless of any stellar encounter? And how would we link a specific shower to a specific star when the evidence is scattered across millions of years and billions of kilometers of space? These questions have driven several independent lines of investigation, each approaching the problem from a different angle. Each reveals something important about the encounter, and each, in its own way, runs into limitations that prevent a definitive answer. The first approach is trajectory reconstruction. This is the method that identified HD 7977 as a potential intruder in the first place, and it remains the most direct way of determining whether a star has passed close to the solar system. The concept is straightforward in principle. You measure a star's current position in the sky, its distance from the sun using parallax, and its three-dimensional velocity using proper motion and radial velocity measurements. You then combine these measurements with a gravitational model of the Milky Way to calculate the star's trajectory backward in time. If the reconstructed trajectory brings the star close to the sun at some point in the past, you have identified a stellar flyby. The execution, however, is extraordinarily challenging. The precision required is extreme. HD 7977 is currently roughly 247 light-years from the Sun. To determine that it passed within a few thousand astronomical units of the Sun 2.5 million years ago, you need to measure its current position to within a fraction of a milliarcsecond on the sky, its distance to within a fraction of a parsec, and its radial velocity to within a fraction of a kilometer per second. Any error in these measurements is amplified enormously when you extrapolate backward over millions of years. A milliarcsecond error in proper motion, when multiplied by 2.5 million years of travel time, translate into an uncertainty of thousands of astronomical units in the calculated closest approach distance. This is not a minor inconvenience. This is the entire difference between a catastrophic flyby and a harmless passing glance. The Gaia spacecraft provides the most precise astrometric measurements ever made for stars brighter than about 21st magnitude. Its positional accuracy reaches below 100 microarcseconds for bright stars, and its proper motion measurements are correspondingly precise. These are extraordinary achievements of engineering and data processing. But even Gaia has limitations, and HD 7977 exposes one of the most important ones. The star's RUBU value of approximately 2.015 is a critical diagnostic. RU stands for Renormalized Unit Weight Error, and it is essentially a measure of how well Gaia's standard astrometric model fits the observed positions of the star over the course of the mission. For a well-behaved single star, the RUI should be close to 1.0. A value significantly above 1.0 indicates that the star's apparent position on the sky varies in ways that the single-star model cannot explain. The most common cause of elevated RU is binarity. If two stars are orbiting each other at a close separation, their combined light creates a single unresolved point source, whose photocenter, the apparent center of light, wobbles back and forth as the two components orbit. This wobble is superimposed on the star's proper motion, contaminating the measurement and introducing systematic errors. If HD 7977 is indeed a binary, then its measured proper motion includes not only the star's true motion through the galaxy, but also the orbital motion of the binary components. When this contaminated proper motion is used to calculate the trajectory backward in time, the result can be significantly wrong. The closest approach distance might be overestimated or underestimated, and the time of closest approach might be shifted by hundreds of thousands of years. Piotr Rybczynski and his colleagues have been at the forefront of analyzing HD 7977's trajectory through multiple iterations of the Gaia catalog. Using Gaia Data Release 2, they obtained one set of orbital parameters. Using Gaia Early Data Release 3, with its improved astrometric solutions, they obtained a significantly different and much closer estimate for the flyby distance. The evolution of the results across data releases illustrates the sensitivity of the calculation to small changes in the input data. With each new data release, the estimated closest approach distance has shifted, sometimes dramatically. This instability is a direct consequence of the RUI issue. Until Gaia can determine whether HD 7977 is a single star or a binary, and correct the proper motion accordingly, the flyby distance will remain deeply uncertain. The researchers Raúl and Carlos de la Fuente Marcos, working independently in Madrid, have performed their own analyses using Gaia Data Release 3. They found that HD 7977 might have passed as close as 0.15 parsecs from the Sun, roughly 31,000 astronomical units, approximately 2.77 million years ago. Their estimates differ somewhat from those of Rybczynski, reflecting different methodological choices and different assumptions about the galactic potential model used for trajectory integration. The disagreement between research groups underscores the fundamental uncertainty. Different teams, using the same data but different analytical frameworks, arrive at different conclusions about the same star. Future Gaia data releases are expected to help resolve this situation. The Gaia mission is planned to continue through approximately 2025, and the final data processing and catalog release are expected later in the decade. The final catalog will include dedicated astrometric solutions for binary and multiple star systems, which should either confirm or rule out the binary hypothesis for HD 7977. If the star turns out to be single, the current close flyby estimates will be strengthened. If it turns out to be binary, the trajectory will need to be recalculated from scratch, and the flyby distance may change by a factor of 10 or more. The numbers are striking when you consider the broad context. Gaia has catalogued nearly 2 billion stars. Among these, Baylor Jones and his colleagues identified hundreds of stars that have passed or will pass within 2 parsecs of the Sun over the past and next several million years. HD 7977 is one among many stellar encounters, but it stands out because of its combination of high mass, potentially small flyby distance, and a timing that coincides with a major geological event. It is not the only known close flyby, but it may be the most consequential if the close distance estimates prove correct. The second approach to investigating the effects of a stellar flyby is dynamical simulation of the Oort Cloud. Rather than looking at the star itself, you build a computational model of the Oort Cloud and ask what would happen to it if a star of a given mass passed at a given distance and velocity. This is the approach taken by Tao, Loeb, and McLeod in their 2025 study, and it is a method with a long history in planetary science. The basic procedure involves creating a numerical model of the Oort cloud, typically consisting of hundreds of thousands to millions of test particles distributed according to some assumed density profile. Each test particle represents a comet nucleus or small icy body. You then introduce a perturbing star on a trajectory defined by the observational data, including its mass, velocity, and closest approach distance, and you integrate the equations of motion forward in time using an n-body simulation code, tracking how the orbits of the test particles change as the star passes through the cloud. After the simulation, you count how many particles have had their perihelia reduced below various thresholds. Those with perihelia below 50 astronomical units will enter the giant planet zone. Those with perihelia below 5 astronomical units will enter the terrestrial planet zone. Those with perihelia below 1 astronomical unit will cross Earth's orbit specifically. From these counts, you can estimate the expected flux of comets into the inner solar system and the probability of impacts on Earth over the duration of the shower. The challenge with this approach is that the results depend heavily on the assumed structure of the Oort cloud, and the Oort cloud structure is one of the least well-constrained features of the solar system. The density profile, the distribution of orbital inclinations, the total number of objects, the boundary between the inner and outer cloud, the mass distribution of the objects, all of these parameters are uncertain by factors of several or more. Different models of the Oort cloud produce dramatically different results for the same stellar flyby. For example, the inner Oort cloud is thought to contain a much higher density of objects than the outer cloud, because objects in the inner cloud are more tightly bound to the Sun and less susceptible to loss through galactic tidal stripping. Models by various research groups have suggested inner to outer cloud population ratios ranging from roughly 3 to 1 up to 10 to 1 or higher. If the inner cloud is densely populated, a close stellar flyby penetrating this region will perturb a very large number of objects, producing an intense comet shower. If the inner cloud is sparsely populated, the same flyby will produce a much weaker shower. The inclination distribution of Oort cloud objects adds another layer of uncertainty. If most objects orbit close to the ecliptic plane, then the geometry of the stellar flyby relative to this plane determines how many objects are strongly perturbed. A star passing through the plane at a low angle will encounter more objects along its path than a star passing at a steep angle. Tsao and colleagues assumed a relatively concentrated inclination distribution near the ecliptic based on recent dynamical models. Other researchers have used more isotropic, spherically symmetric distributions, which tend to produce somewhat weaker showers for the same flyby parameters, because the objects are spread over a larger volume of space. Despite these uncertainties, the simulations consistently show that a solar mass star passing within a few thousand astronomical units of the Sun would produce a significant enhancement in the long-period comet flux. The question is not whether a close flyby would cause a comet shower. The physics is clear on that point. The question is how intense the shower would be, how long it would last, and whether the effects would be detectable in the geological or astronomical record. The third approach involves searching for direct evidence of enhanced cometary activity in Earth's geological record. If comet shower occurred approximately 2 to 2.5 million years ago, it should have left traces. Impact craters on land, tektite fields, which are strewn fields of natural glass produced by the heat of an impact, layers of extraterrestrial material in ocean sediments containing elevated concentrations of iridium, osmium, and other elements that are rare in Earth's crust but common in comets and asteroids. Any or all of these could potentially be linked to a period of enhanced bombardment. The evidence is tantalizing but sparse. The Eltanin impact, dated to approximately 2.5 million years ago, is the most prominent candidate. A large body, estimated at 1 to 4 kilometers in diameter, struck the ocean floor in the Bellingshausen Sea, an area of the southeastern Pacific near Antarctica. The impact occurred in deep water, roughly 5,000 meters below the surface, and produced no visible crater on the seafloor. But it left a characteristic layer of iridium-enriched sediment and fragments of meteoritic material that has been recovered from ocean drilling cores. The timing, within a few 100,000 years of the Pliocene-Pleistocene boundary, is suggestive. However, subsequent chemical analysis by Taggel and Clays in 2004 indicated that the Eltanin impactor was likely an asteroid, based on its siderophile element ratios, rather than a comet. Comets and asteroids have distinct chemical signatures, and the Eltanin material appeared more consistent with a chondritic asteroid than with a cometary nucleus. This does not entirely rule out a connection to a comet shower, but it means that the most prominent impact event from this time period may not be directly linked to HD 7977's passage. Other possible impact evidence from the late Pliocene is less well documented. A few tektite fields and impact glass deposits have been tentatively dated to this period, but the dating is often imprecise, and the connection to a specific impact event is uncertain. The overall impact record for the Pliocene is less thoroughly studied than for more recent geological periods, or for the dramatic Cretaceous-Paleogene boundary, partly because the impacts may have been smaller and their traces more easily erased by erosion, sedimentation, and geological processes. There is also a fundamental observational bias. Roughly 70% of Earth's surface is ocean. Impacts into the ocean leave much less permanent evidence than impacts on land. A comet striking the deep ocean would produce a transient tsunami, deposit a thin layer of impact debris on the seafloor, and excavate a crater that would be destroyed by seafloor spreading within a few tens of millions of years. Unless a deep-sea drilling expedition happens to sample the right piece of seafloor at the right depth, the evidence will never be found. The absence of a clear impact record does not mean the shower did not occur. It may simply mean we have not looked in the right places, or that the evidence has been destroyed. The fourth approach is to examine the comets themselves. If HD 7977 triggered a comet shower 2.5 million years ago, some of the comets from that shower should still be arriving in the inner solar system today. They would be on extremely long-period orbits, with periods of millions of years. Their orbital elements, the mathematical parameters that define the shape, size, and orientation of their orbits, should bear the fingerprints of the gravitational perturbation caused by the passing star. Dybczynski and Krolikowska have examined the orbits of known long-period comets to search for such signatures. Their method involves tracing the orbits of observed comets backward in time, accounting for the gravitational perturbations of the planets, to determine the comet's original orbital parameters when they were in the distant Oort Cloud, before they entered the inner solar system. If a group of comets shares similar original orbital elements, particularly similar semi-major axes, and orbital orientations that are consistent with perturbation from a specific direction at a specific time, then those comets may be part of a shower triggered by a known stellar encounter. Their analysis identified several long-period comets whose original orbital elements are broadly consistent with perturbation by a solar mass star passing through the inner Oort cloud in approximate direction and at the approximate time of HD 7977's calculated trajectory. The evidence is suggestive but not conclusive. The sample of known long-period comets is small, numbering in the hundreds, compared to the trillions of objects in the Oort cloud. The comets we observe are a tiny, heavily biased sample of the overall population, consisting only of those that happen to be perturbed onto orbits that brought them close enough to the Sun to become visible. Drawing statistical conclusions about the Oort cloud as a whole from this small sample is fraught with difficulty. Moreover, long-period comets are affected by non-gravitational forces, particularly outgassing, which alters their trajectories as they approach the Sun. Accounting for these forces when tracing orbits backward introduces additional uncertainty, and the gravitational perturbations of the planets, particularly Jupiter and Saturn, can significantly modify a comet's orbit during its passage through the inner solar system, making it harder to recover the original pre-perturbation orbital elements. Despite these challenges, the orbital analysis of long-period comets remains one of the most promising avenues for confirming or refuting the HD 7977 comet shower hypothesis. As more long-period comets are discovered and their orbits are measured with increasing precision, the statistical power of this approach will grow. The fifth approach is comparative. If stellar flybys can trigger comet showers, then HD 7977 is not the only star worth examining. Comparing it to other known flybys, both past and future, helps place its potential effects in context and sharpens our understanding of what factors determine the severity of an encounter. The most famous past flyby is that of Schultz's star, a dim binary system consisting of a red dwarf with a mass roughly 8% of the Sun's and a brown dwarf companion with roughly 6% of the Sun's mass. In 2015, Eric Mamajek at the University of Rochester and an international team of collaborators published a paper demonstrating that Schultz's star passed through the outer Oort Cloud approximately 70,000 years ago. The system came within roughly 52,000 astronomical units of the Sun, or about 0.82 light-years. This is well within the outer Oort Cloud, but far from the inner cloud, where the highest density of objects is expected to reside. Despite the relative closeness of the encounter by cosmic standards, the gravitational effects of Schultz's star on the Oort Cloud were almost certainly minimal. The total mass of the system is only about 15% of the Sun's mass. Gravitational perturbation scales with the mass of the perturber and inversely with the square of the distance. A low-mass perturber at a distance of 52,000 astronomical units simply does not exert enough gravitational force to significantly alter the orbits of Oort Cloud objects. The velocity change imparted to any individual comet nucleus would be tiny, a fraction of a meter per second, far too small to meaningfully change its orbital parameters. Mamajek's team acknowledged this, noting that the encounter was unlikely to produce a detectable increase in the long-period comet flux. Nathan Kaib, an expert on Oort Cloud dynamics at the University of Oklahoma, confirmed this assessment, stating that the effect on the long-period comet flux would be minimal. Schultz's star is historically important as the closest known stellar flyby in relatively recent times, but it was not close enough or massive enough to pose a significant threat. Nevertheless, there is evidence that even this modest encounter left a detectable trace. In 2018, researchers Carlos and Raúl de la Fuente Marcos, brothers working at the Complutense University of Madrid, along with Sverre Arseth of the University of Cambridge, published a study examining the orbits of nearly 340 objects in the solar system with hyperbolic or near-hyperbolic orbits. They found a statistically significant clustering of orbital radiants, the directions from which these objects appear to originate, in the constellation Gemini. This clustering is consistent with the direction from which Schultz's star approached the solar system. The implication is that the flyby, despite being relatively distant and low mass, did leave a subtle but detectable imprint on the orbits of some outer solar system bodies. Now compare Schultz's star with HD 7977. If HD 7977 passed within 3,000 astronomical units of the Sun, it was roughly 17 times closer than Schultz's star. Its mass, approximately 1.07 solar masses, is roughly 7 times the total mass of the Schultz's star system. The gravitational perturbation scales roughly as mass divided by the square of distance, so HD 7977's effect would have been on the order of 7 times 17 squared, which is roughly 2,000 times stronger than that of Schultz's star. 2,000 times stronger. If Schultz's star could leave a detectable trace despite being weak enough that experts described its effects as minimal, then the effect of HD 7977, if it truly passed within a few thousand astronomical units, would have been overwhelming. The comparative study of stellar flybys has revealed another important insight: the role of stellar velocity. A star that moves slowly relative to the Sun spends more time within the Oort Cloud, and its gravitational influence has more time to act on individual cometary bodies. This extended interaction time produces larger velocity impulses and more dramatic orbital changes. Conversely, a star moving at high velocity passes through the cloud quickly, delivering a brief, sharp gravitational tug that produces smaller perturbations. This velocity effect explains why some stellar encounters that are relatively distant can still produce significant effects, while some close encounters might be less consequential than expected. Schultz's star, for example, passed close to the outer Oort cloud, but moved at a relatively high velocity. estimated at roughly 80 kilometers per second relative to the Sun. This high speed limited its interaction time and reduced the total impulse delivered to Oort Cloud objects. HD 7977, by contrast, appears to have been moving at a more moderate velocity of roughly 20 to 30 kilometers per second. This slower speed, combined with its closer approach distance, amplifies its potential impact. The slower the intruder moves, the longer it lingers, and the deeper it reaches into the cloud's population of loosely bound bodies. There is also the question of the intruding star's own planetary system. We know nothing about whether HD 7977 has planets, a debris disk, or a cloud of its own icy bodies. If the star carried its own retinue of small bodies, the flyby might have involved a mutual exchange of material. Comets from HD 7977's system could have been deposited into our Oort Cloud, while some of our Oort Cloud objects could have been captured by the passing star. This possibility, while speculative, is consistent with the birth cluster hypothesis for Oort Cloud formation. The exchange of material between stellar systems during close encounters may be a routine process in the galaxy, occurring every few million years wherever stars pass close to one another. If so, the Oort Cloud is not just a relic of our own solar system's formation. It is a living archive, continuously refreshed by contributions from passing stars, each flyby adding a new geological layer to the frozen library that surrounds us. The search for additional evidence of HD 7977's passage extends beyond orbital mechanics. Researchers have also looked for geological signatures on Earth that might correspond to the predicted timing of the comet shower. The geological record preserves evidence of cosmic impacts in the form of impact craters, tektite fields, layers of shocked minerals, and spikes in the concentration of extraterrestrial elements such as iridium and osmium in marine sediments. The chemical composition of comets that might be traced back to the HD 7977 encounter also offers potential avenues for investigation. Long-period comets from different regions of the Oort Cloud may carry distinct chemical fingerprints, reflecting the conditions under which they formed and the extent to which they have been processed by cosmic radiation during their billions of years in deep space. The ratio of deuterium to hydrogen in cometary water, the abundance of noble gases, and the complexity of organic molecules all carry information about a comet's history. If a cluster of long-period comets arriving from similar orbital geometries shares unusual chemical signatures, it could constitute evidence that they were perturbed from the same region of the Oort Cloud by a specific gravitational event. Current ground-based and space-based spectroscopic capabilities are sufficient to measure some of these signatures, though the rarity of bright long-period comets limits the sample size available for study. Every long-period comet that passes through the inner solar system in the coming decades represents an opportunity to test the predictions of the flyby models, a frozen archive from the deep past that, if read carefully, could confirm or refute the story that the orbital mechanics tell. Consider now the future encounter with Gliese 710. This K-type dwarf star, currently about 62 light-years away in the constellation Serpens Cauda, is headed directly toward us. In approximately 1.29 million years, it will pass within roughly 10,600 astronomical units of the Sun, about 0.051 parsecs. This will bring it well within the outer Oort Cloud and to the outskirts of the inner cloud. Gliese 710 has a mass of approximately 60% of the Sun's mass. Its closest approach distance, around 10 to 11,000 astronomical units, places it at the boundary between the inner and outer Oort Cloud. Bersky and Dybczynski, analyzing Gaia data in 2016, described the future encounter with Gliese 710 as potentially the strongest disrupting encounter in the future and history of the solar system. Their simulations showed that the flyby would generate a large flux of new long-period comets, with approximately 10 naked-eye comets per year arriving in the inner solar system for a period of 3 to 4 million years after the encounter. 10 naked-eye comets per year for millions of years. This is a fundamentally different sky than the one we see today, where a bright naked-eye comet is an event that happens perhaps once every 5 to 10 years. The solar system, after Gliese 710's passage would be a transformed place, with comets streaming inward from all directions, some of them crossing the orbits of the planets, a small fraction of them potentially on collision courses with Earth. But even Gliese 710 may not be the most consequential encounter. If HD 7977 truly passed within 3,000 astronomical units, it was both closer and more massive than Gliese 710. Its effects on the inner Oort cloud would have been substantially greater. The resulting comet shower would have been more intense, longer lasting, and potentially more devastating than anything Gliese 710 will produce. There is also the star UCAC 4237-008148, identified by the De La Fuente Marcos brothers using Gaia Data Release 3. This star, with a well-behaved RU of 0.927, appears to have passed within approximately 0.259 parsecs of the Sun, about 53,000 astronomical units, roughly 1.16 million years ago. That is closer than the median estimate for Schultz's star, but still comfortably within the outer Oort cloud. Its low mass means the perturbation was probably modest, but it adds another entry to the growing ledger of stellar visitors. There is yet another dimension to the comparative analysis that deserves attention: the question of how stellar flybys interact with the galactic tide. The galactic tide is not constant. It varies depending on the Sun's position in the Milky Way, which changes as the Sun orbits the galactic center every 225 to 250 million years. When the Sun passes through the dense midplane of the galactic disk, the tidal force is strongest. When the Sun is above or below the midplane, the tidal force weakens. This oscillation in the galactic tide has a period of approximately 30 to 40 million years, corresponding to the Sun's vertical oscillation through the disk. Some researchers have suggested that this oscillation may correlate with periodic increases in the rate of cometary bombardment on Earth, as the enhanced tidal force during midplane crossings sends additional Oort cloud objects cascading into the inner solar system. The idea of periodic mass extinctions, first proposed by David Raup and John Sepkoski in 1984, has been debated for decades, and the galactic tide oscillation is one of the proposed mechanisms for driving such periodicity. Stellar flybys add a stochastic random component on top of this periodic tidal forcing. A close stellar encounter can produce a comet shower that is superimposed on the background flux, driven by the galactic tide. If a close encounter happens to occur near a mid-plane crossing, when the tidal force is already elevated, the combined effect could be particularly devastating, producing a more intense and longer-lasting shower than either mechanism would produce alone. Whether HD 7977's flyby coincided with such a tidal maximum is not well constrained, but the possibility adds another layer of complexity to the story. The interaction between tidal forcing and impulsive stellar perturbations is an active area of research. Simulations by multiple groups have shown that the two mechanisms can work synergistically, with tidal torquing slowly bringing Oort cloud objects into configurations where they are more susceptible to perturbation by a passing star. Conversely, a stellar flyby can scatter objects into orbits where the galactic tide can more efficiently deliver them to the inner solar system. The result is a complex, coupled system in which the timing and intensity of comet showers depend not just on the parameters of individual stellar encounters, but on the broader galactic context in which those encounters occur. This complexity means that simply knowing HD 7977's closest approach distance is not enough to predict the resulting comet shower with precision. You also need to know the state of the galactic tide at the time of the flyby, the prior history of the Oort cloud, including any previous stellar encounters that might have reshaped it, and the detailed structure of the inner cloud. All of these factors are uncertain, and all of them contribute to the range of possible outcomes. It is worth noting one additional piece of evidence that bears on the story. In the solar system today, there is an object whose very existence may testify to a past close stellar encounter, the dwarf planet Sedna, discovered in 2003 by Michael Brown, Chad Trujillo, and David Rabinowitz. Sedna orbits the Sun on an extremely elongated orbit with a perihelion of roughly 76 astronomical units, and an aphelion of roughly 937 astronomical units. Its orbital period is approximately 11,400 years. Sedna's perihelion is too distant for any of the known planets to have placed it in its current orbit through gravitational scattering. Something else must have been responsible. One of the leading hypotheses is that Sedna's orbit was shaped by a close stellar flyby during the early history of the solar system, when the Sun was still embedded in its birth cluster and stellar encounters were much more frequent. The passing star would have pulled Sedna outward from a more circular orbit in the Kuiper Belt region, stretching its orbit into the elongated ellipse we observe today. If this hypothesis is correct, Sedna is a fossil of a stellar encounter that occurred over 4 billion years ago, a permanent scar on the solar system's architecture, left by a star whose identity has been lost to time. Sedna's existence reminds us that stellar flybys do not just produce temporary comet showers. They can permanently alter the orbital structure of the solar system's outer regions. Every distant body on an anomalous orbit is a potential witness to an encounter we have yet to identify. If HD 7977 came close enough, its effects on the Oort Cloud and the trans-Neptunian region may still be detectable today in the orbital distribution of distant bodies. This is another avenue of investigation that future surveys of the outer solar system, such as those expected from the Vera C. Rubin Observatory, may be able to pursue. The math is striking. If significant Oort cloud perturbation requires a flyby within roughly 5,000 astronomical units by a solar mass star, and if such events occur on average once every 50 to 100 million years, then over the 4.6 billion year history of the solar system, there have been roughly 46 to 92 such events. 46 to 92 intense comet showers, each lasting 1 to several million years, each enhancing the impact rate on Earth by factors of 5 to 10. These showers overlap with the steady background of comet arrivals, producing a complex, fluctuating bombardment history that has been one of the defining features of the inner solar system's evolution. We have identified and studied perhaps half a dozen of these encounters. The rest are lost in deep time, their perpetrators scattered across the galaxy, their comet showers long since subsided, their impacts buried beneath billions of years of geological activity. HD 7977 is one of the very few we can name, one of the few whose trajectory we can trace, one of the few whose consequences we can begin to estimate. It is a window into a process that has been operating for as long as the solar system has existed, and we are only now, with the data from Gaia and the computational tools of modern astrophysics, beginning to understand how that process has shaped the world we live on. There is a deeper truth buried in the story of HD 7977, and it goes beyond the specifics of one star, one flyby, one possible comet shower. The deeper truth is about vulnerability. Our solar system is not a fortress. It is not a sealed vault, protected from the galaxy by some barrier or boundary. It is an open system, continuously interacting with the galactic environment that surrounds it on all sides. And the most fragile part of that system, the Oort cloud, is also the part that connects us most directly to the rest of the cosmos. Think about what the Oort cloud represents. It is a reservoir of primordial material left over from the formation of the solar system 4.6 billion years ago. During the early, chaotic phase of planetary formation and migration, when the giant planets were shifting their orbits and jostling for position, vast quantities of icy material were flung outward from the region around the Sun. These objects, too small and too numerous to coalesce into planets, were ejected on long, looping orbits that carried them to enormous distances. Over time, the gravitational influence of the galaxies and passing stars circularized some of their orbits, trapping them in the distant cloud where they have remained ever since. They are time capsules, frozen remnants of the solar system's birth, preserved by the deep cold of interstellar space at temperatures just a few degrees above absolute zero. But the Oort cloud is not merely a museum of ancient material. It is an active participant in the ongoing evolution of the solar system. Through the twin mechanisms of the galactic tide and stellar encounters, it continuously supplies the inner solar system with long-period comets. These comets, when they approach the Sun, sublimate and release gas and dust, creating the spectacular tales that have inspired wonder, fear, and superstition in every human civilization that has looked up at the sky. Some of these comets pass harmlessly through the inner solar system and return to the outer darkness. Others are captured into shorter period orbits by gravitational interactions with the giant planets. And a small fraction, over the billions of years of the solar system's history, have struck the surfaces of planets, including ours. There is a growing body of evidence suggesting that cometary and asteroidal impacts played a significant role in shaping the early Earth. The late heavy bombardment, a period of intense impact activity that occurred roughly 4.1 to 3.8 billion years ago, is thought to have been driven in part by the gravitational restructuring of the giant planets' orbits, which scattered enormous quantities of material, both inward and outward. But some of that material may also have originated in the Oort Cloud, disturbed by stellar encounters during the solar system's passage through the denser stellar environment of its birth cluster. Comets are thought to have delivered significant amounts of water and organic molecules to Earth's surface during and after the late heavy bombardment. The isotopic composition of water in some comets, particularly those of the Jupiter family, is similar to that of Earth's oceans, while the exact fraction of Earth's water that was delivered by comets remains a subject of active research, with estimates ranging from a small percentage to a substantial fraction. The role of cometary delivery in establishing the conditions for life is widely acknowledged. Let that sink in. The very mechanism that threatens us with destruction, comets falling inward from the Oort cloud, is also the mechanism that helped make our world habitable. The water you drink, the oceans that cover 70% of Earth's surface, the organic chemistry that underpins every living cell, some fraction of all of this was delivered from the outer darkness by icy bodies that fell sunward over billions of years. The Oort cloud is both a cradle and a weapon. Its comets bring the ingredients for life to the inner solar system. And when those comets arrive in excess, driven inward by the gravity of a passing star, they can extinguish life on a global scale. Consider for a moment the sheer improbability of our situation. We live on a planet that is positioned at just the right distance from its star for liquid water to exist on the surface. Our planet has a magnetic field that shields us from the solar wind. It has an atmosphere thick enough to retain warmth, but transparent enough to allow starlight through. It orbits a star that is stable enough to have burned steadily for 4.5 billion years without dramatic fluctuations in luminosity. And it is surrounded by a system of giant planets, particularly Jupiter and Saturn, whose gravitational influence helps to shield the inner solar system from some fraction of incoming comets and asteroids, sweeping them up or deflecting them before they can reach us. All of these conditions are necessary for complex life to exist, and yet, even with all of these protections in place, the solar system remains vulnerable to external perturbation. The Oort cloud sits beyond the protective influence of the giant planets. A comet perturbed from the Oort cloud into the inner solar system must run a gauntlet of gravitational encounters with Jupiter and Saturn before it can reach Earth. Jupiter, with its enormous mass, acts as a gravitational vacuum cleaner, capturing or deflecting many incoming comets. But its protection is not absolute. Long-period comets arrive on orbits that are highly inclined relative to the ecliptic and that approach the Sun from all directions. Many of them pass above or below Jupiter's orbit entirely, never coming close enough to the giant planet to be significantly deflected. The result is that while Jupiter reduces the rate of cometary impacts on Earth, it does not eliminate them. A comet shower triggered by a close stellar flyby will produce a much larger number of incoming comets than usual, and a larger fraction of them will slip past Jupiter's gravitational defenses simply because there are more of them. The protective effect of Jupiter becomes less effective during periods of enhanced bombardment, precisely when it is needed most. This is a sobering irony. The shield that protects us during normal times is overwhelmed during the very crises that pose the greatest danger. This duality is not unique to the Oort cloud. It is a recurring theme throughout the cosmos. The same nuclear fusion reactions that power the Sun and make life on Earth possible also power the explosive deaths of massive stars in supernovae events that can sterilize entire regions of the galaxy. The same plate tectonics that recycles Earth's crust, regulates atmospheric carbon dioxide, and maintains a habitable climate also causes earthquakes and volcanic eruptions that can devastate civilizations. The universe does not distinguish between creation and destruction. They are not opposites. They are aspects of the same underlying processes, different manifestations of the same physical laws operating at different scales and timescales. Now consider the spatial scale of the Oort Cloud and what it means for our relationship with the galaxy. The outer edge of the Oort Cloud lies at roughly 100,000 astronomical units from the Sun. That is approximately 1.6 light-years. The nearest star system, Alpha Centauri, consisting of two Sun-like stars, and the red dwarf Proxima Centauri, is about 4.2 light-years away. The Oort Cloud therefore extends roughly 40% of the way to the nearest star. It is not a compact bubble enclosing the planetary system. It is a vast, diffuse halo that reaches deep into the interstellar medium, the thin gas and dust that fills the space between stars. Objects at the outer edge of the Oort Cloud are as gravitationally influenced by the galaxy as a whole as they are by the Sun specifically. They exist in a twilight zone, a transitional region between the solar system's gravitational domain and the broader gravitational field of the Milky Way. Their orbits are shaped by both. They belong to both and to neither. They are the most marginal members of our solar system, the last outpost before interstellar space begins. Let that sink in. Nearly half the distance to the nearest star is occupied by the most fragile and extended part of our solar system, and any star that passes within a light-year or so of the Sun can reach into this region and rearrange it. The frequency of such encounters is not as rare as you might hope. Using Gaia data, Baylor Jones and his team estimated that roughly 20 stars pass within 1 parsec of the Sun every million years. Over the course of 1 billion years, that amounts to roughly 20,000 stellar encounters within 3.26 light-years. Over the full 4.6 billion year history of the solar system, that would be roughly 92,000 such encounters. The vast majority of these involve low-mass stars passing through the outer reaches of the Oort Cloud at high speed, producing negligible perturbations. But a subset, perhaps 1 in 1,000, involve more massive, slower-moving stars penetrating deeper into the cloud. And these are the encounters that can produce detectable, consequential effects. The cumulative effect of all these encounters, spread over billions of years, is to gradually erode the Oort Cloud from the outside in. Each passing star strips away some objects, either ejecting them from the solar system entirely or deflecting them inward toward the Sun, where they are eventually destroyed by solar heating, ejected by planetary encounters, or smashed into the surfaces of planets and moons. The galactic tide contributes to this erosion as well, continuously torquing orbits and feeding the slow, steady drizzle of long-period comets into the inner solar system. The Oort Cloud that exists today is therefore smaller than the one that existed during the solar system's youth. It has been losing members for billions of years, and while it is being replenished to some degree by objects scattered outward from the Kuiper belt by the giant planets, this replenishment operates much more slowly than the loss. The Oort Cloud is a diminishing asset, a finite resource that the solar system is gradually spending down. Eventually, over timescales of tens of billions of years, it will be depleted to insignificance. When that happens, long-period comets will cease to arrive in the inner solar system, and one of the most ancient and spectacular features of our night sky will disappear forever. But that exhaustion lies far in the future. The more immediate truth is that the Oort Cloud is here now. It is enormous, and it is vulnerable to external perturbation. This is not science fiction. This is observed reality, confirmed by the best astrometric data ever collected by human instruments. Stars are passing near the solar system all the time. We can measure their trajectories, calculate their closest approach distances, model their effects on the Oort Cloud, and estimate the resulting flux of comets into the inner solar system. Scholz's star came through the outer cloud roughly 70,000 years ago. HD 7977 may have ploughed through the inner cloud 2.5 million years ago. Gliese 710 will arrive in about 1.3 million years. These are not possibilities. They are certainties, or near certainties, derived from precise measurements of real objects, and each of these encounters has the potential to alter the population of long-period comets in the inner solar system. The enhanced flux from a single close encounter can persist for millions of years after the star has passed. We may, at this very moment, be living through the fading tail of a comet shower triggered by HD 7977's passage. We cannot be certain because the background rate of long-period comet arrivals is poorly constrained, and the expected enhancement from a moderately distant flyby would be subtle, perhaps only a factor of 2 or 3 above the normal rate. We would not notice. The comets would arrive one at a time, separated by centuries or millennia, indistinguishable from the ordinary background flux, unless we had a baseline to compare against. And we do not have that baseline. The uncertainty is itself unsettling. We do not know how many long-period comets are currently falling toward the inner solar system, perturbed from the Oort Cloud by encounters we have not yet identified. We do not know how many of those comets will cross Earth's orbit in the coming centuries and millennia. We do not know their sizes, their trajectories, or their arrival times. The Oort Cloud is simply too far away, too dark, and too vast for us to survey with existing technology. We can only detect its members when they are already falling inward, brightening as they approach the sun, typically with only months to years of warning. There is a paradox at the heart of this story. The greatest long-term threat to life on Earth from space may not come from the asteroid belt, which is relatively well catalogued, or from the near-Earth object population, which we are actively surveying with ground-based and space-based telescopes. It may come from the Oort Cloud, a region we cannot see, cannot map, and can barely study. And the trigger for that threat is not an internal process within the solar system. It is an external event, the passage of a star through our neighborhood that we have no ability to prevent, deflect, or avoid. We can deflect an asteroid. NASA's DART mission successfully altered the orbit of the small asteroid Dimorphos in September of 2022, demonstrating that directed kinetic impact can change the trajectory of a small body if we detect the threat early enough. But we cannot deflect a star. We cannot alter the trajectory of a solar mass body, traveling at tens of kilometers per second through the galaxy. We can only observe it, measure it, model its effects, and wait. The question of what the Oort Cloud means for the long-term survival of complex life on Earth is one that does not lend itself to simple answers. On one hand, the fossil record shows that life on this planet has endured for nearly 4 billion years, surviving multiple mass extinctions, sustained volcanic episodes, and dramatic swings in climate. The biosphere is resilient. Even the Chicxulub impact, which killed 75% of all species on Earth, did not sterilize the planet. Life recovered, diversified, and eventually produced the intelligence that allows us to reconstruct these ancient catastrophes. On this view, the Oort Cloud is a manageable risk, one of many hazards that life on Earth has learned to absorb and survive. But there is a countervailing perspective. The 5 billion years that remain before the Sun exhausts its hydrogen fuel is a long time, and the probability of encountering a very close stellar flyby during that span is not negligible. A flyby significantly closer than HD 7977's, one that penetrates deep into the inner Oort Cloud at a distance of perhaps 500 or 1,000 astronomical units, could produce a comet shower of unprecedented intensity, potentially delivering dozens or hundreds of large impactors to the inner solar system over a period of several million years. Such an event could overwhelm even the biosphere's considerable resilience. There is a deeper irony in the relationship between the Oort Cloud and the prospects for life in our solar system. The same reservoir of icy bodies that may have seeded Earth with water and organic molecules in the distant past now represents the single greatest reservoir of potential impactors in the solar system. The comets that brought the ingredients for life are chemically and physically identical to the comets that could end it. They are the same objects, on the same orbits, in the same cloud. The only difference is timing. A comet that arrived 4 billion years ago and delivered water to the young Earth was a gift. A comet that arrives tomorrow on a collision course is a catastrophe. The cloud does not distinguish between creation and destruction. It simply exists, a vast, patient reservoir of possibility, waiting for gravity to decide which role each frozen body will play. There is one more aspect of this story that deserves consideration: the question of preparedness. At present, humanity's efforts to defend against impact threats are focused almost entirely on near-Earth asteroids, objects in the asteroid belt or the inner solar system whose orbits bring them close to Earth. Programs like NASA's Planetary Defense Coordination Office and the European Space Agency's Space Safety Program maintain catalogues of known near-Earth objects and monitor their orbits for potential future impacts. These programs have been remarkably successful. As of the mid-2020s, more than 34,000 near-Earth asteroids have been discovered and tracked, and the vast majority of objects larger than 1 kilometer have been identified and determined to pose no threat for at least the next century. But long-period comets from the Oort Cloud represent a blind spot in this defense architecture, because they arrive from all directions and on orbits that bring them into the inner solar system for the first time. They cannot be catalogued in advance. They are only detected when they are already falling inward, typically when they are within a few astronomical units of the Sun and their ices begin to sublimate, producing the characteristic coma that makes them visible. This gives us, at best, a few months to a few years of warning before a long-period comet reaches Earth's orbit. For a large, fast-moving cometary nucleus, that may not be enough time to mount a deflection mission. The DART mission demonstrated that kinetic impact can alter the orbit of a small body, but DART targeted a slow-moving, well-characterized asteroid in a known orbit, with years of preparation time. Deflecting a long-period comet discovered only months before its closest approach to Earth would be an enormously more difficult challenge, requiring rapid response launch capabilities and deflection technologies that do not yet exist. This is the technological gap that the HD 7977 story highlights. We are building defenses against the threats we can see, but the threats we cannot see, the comets falling silently inward from the depths of the Oort Cloud, remain beyond our reach. The timescales involved in this story deserve one final moment of reflection. The light from HD 7977 takes roughly 247 years to reach us. That means when we observe this star tonight through a telescope, we are seeing it as it was in the late 18th century. Before the French Revolution, before the discovery of Neptune, before the theory of evolution. The flyby itself occurred 2.47 million years ago, a span of time that is almost beyond comprehension. If you were to count to 2.47 million, speaking one number per second without stopping, it would take you roughly 28 days. If each second represented a year, you would count for 78 years without pause, an entire human lifetime, before reaching the moment when HD 7977 swept through the Oort Cloud, and yet the effects of that ancient encounter may still be unfolding. Comets, perturbed by the flyby, are still falling inward, on orbits so vast that they have not yet completed their first journey to the inner solar system. Some of them will arrive centuries from now, others will arrive millennia from now. The shower is not over, it is merely fading, growing quieter with each passing epoch, like the last reverberations of a bell struck millions of years ago. We live inside that fading echo. Every long-period comet that crosses our sky is a potential messenger from an encounter that our species was not present to witness, but whose consequences we inherit. This places the story of HD 7977 in an unusual category among scientific narratives. It is not a story about something that happened in the distant past and ended. It is a story about something that began in the distant past and continues. The comet shower it triggered is a process, not an event. It has a beginning but no sharp ending, only a gradual diminishing that stretches across geological time. We are not observers of this story. We are participants in it, living within the extended aftermath of a gravitational encounter that shaped the conditions of our planet and that may yet deliver further surprises from the frozen depths of the outer solar system. The story of HD 7977 teaches us something fundamental about our place in the universe. Our solar system is not a closed room with locked doors and sealed windows. It is an open structure, embedded in a dynamic galactic environment, subject to forces and visitors that originate far beyond the orbit of the outermost planet. The Gaia mission has given us our first detailed map of these forces and visitors, and what the map reveals is both thrilling and sobering. The galaxy is full of travelers. Some of them have already passed through our home, and others are on their way. What does all of this mean for us? For humanity, standing on the surface of a small rocky planet, orbiting a middle-aged star in the quiet suburbs of an unremarkable spiral galaxy. What does it mean to know that 2.5 million years ago, before our species existed, before our genus had fully emerged, a star wandered through our cosmic neighborhood and may have changed the trajectory of life on Earth in ways we are only beginning to understand? It means, first, that we are more deeply connected to the galaxy than we ever imagined. For most of human history, the stars were a backdrop, a canopy of fixed lights that rotated overhead with comforting regularity. Even after Copernicus and Kepler and Newton revealed that the stars were distant suns governed by the same laws of physics that govern the falling of an apple, the assumption persisted that they were fundamentally separate from us. They were objects to be studied, catalogued, classified, but not feared, not considered as active participants in the ongoing evolution of our world. The story of HD 7977 challenges that assumption in the most direct way possible. The stars are not fixed, they move, they wander, and their wanderings have consequences that reach across light years and millennia to touch the surface of our planet. It means, second, that the history of life on Earth is not purely an internal story. The textbook narrative of evolution presents a drama played out entirely on the surface of our planet, driven by genetics, natural selection, continental drift, volcanism, and climate change. These are all real and important forces, but they operate within a larger context, a galactic context that includes external perturbations from passing stars, cometary impacts, and other cosmic events. If HD 7977 did trigger a comet shower that contributed to the Pliocene-Pleistocene climatic shift, then the ice ages that shaped our world were not solely the product of terrestrial processes. They were influenced by an event that occurred in the depths of space, at distances far beyond anything that our ancestors could have perceived or imagined. The implications of this are profound. The ice ages created the climatic instability that drove the evolution of the genus Homo. The alternation of glacial and interglacial periods, selected for intelligence, adaptability, and social cooperation, traits that allowed our ancestors to survive in a world of rapid environmental change. If HD 7977's comet shower was one of the factors that tipped the climate system into the glacial-interglacial cycle, then the emergence of our species was influenced, however indirectly, by the gravitational pull of a star that no living creature on Earth could see. We are, in the most literal sense, children of the galaxy. Our existence was not determined solely by the chemistry of Earth's crust or the biology of our cells. It was shaped by events that occurred in the immense spaces between stars. Pause on that for a moment. A star that passed by 2.5 million years ago, noticed by no one, recorded by nothing, may have helped create the conditions in which human intelligence evolved. The gravity of that star, acting on frozen bodies at the edge of the solar system, may have contributed to the chain of events that eventually produced a species capable of looking back through time and identifying the star that may have helped create it. There is a circularity to this that borders on the poetic. The universe creates the conditions for minds to arise, and those minds then discover the mechanisms by which they were created. It means, third, that we are living in a period of relative calm that will not last forever. The Oort Cloud is always being stirred. Most of the time, the stirring is gentle, producing only a slow trickle of long-period comets. But periodically, the stirring intensifies. A close encounter with a massive star produces a sustained flood that can last for millions of years. The last such flood may have been triggered by HD 7977. The next may be triggered by Gliese 710. Between these events, we exist in a lull, a window of relative safety that is defined not by any intrinsic stability of the solar system, but by the accident of no massive star happening to pass close enough to trigger a significant shower. We are temporary residents in a temporary calm. The galaxy moves on its own schedule, indifferent to our concerns, and the next encounter is always approaching, somewhere out there beyond the range of our telescopes, drifting along its own galactic orbit. There is something humbling about this realization. We spend our days focused on the immediate and the tangible. We worry about weather and economics and politics and the thousand small dramas of human life. These concerns are real and legitimate, but they exist within a framework of assumed permanence, a background belief that the physical stage on which our lives play out will remain essentially unchanged for the foreseeable future. The story of HD 7977 reminds us that this assumption has limits. Not today, not next year, perhaps not for another million years, but eventually something will come along that tests the resilience of our world in ways we have not yet experienced. And there is something beautiful about it too. We are not merely observers of the cosmos, peering through telescopes at distant objects that have no connection to our daily lives. We are participants. We are made of matter that was forged in stars, living on a planet that was shaped by cometary impacts, inhabiting a world whose climate was influenced by stellar encounters. The same gravitational forces that carved the Oort Cloud and sent comets falling toward the Sun also carried our Sun on its 4.5 billion-year journey around the Milky Way, past stars and nebulae and molecular clouds, through spiral arms and inter-arm gaps, in an orbit that will continue long after our civilization has ended. Consider one final scaled comparison. If the age of the solar system, 4.6 billion years, were compressed into a single calendar year, with the solar system forming on January 1st and the present day falling on December 31st at midnight, then HD 7977's flyby occurred at approximately 11:41 p.m. on December 31st, less than 20 minutes before the present moment. And the emergence of our species, Homo sapiens, roughly 300,000 years ago, occurred at approximately 11:59 p.m. and 57.9 seconds, 3 seconds before midnight. The entirety of human civilization, from the first cave paintings to the launch of the Gaia spacecraft, occupies less than a second on this calendar. We are the newest arrivals at a party that has been running for an entire year, and the star that may have helped set the conditions for our arrival passed through the room just minutes before we walked in. The Gaia mission has given us the ability to see these cosmic visitors for the first time, to trace their paths, to name them, to begin understanding their effects. This is one of the great scientific achievements of the early 21st century, and we are still in its opening chapters. The best Gaia data is yet to come. The final catalogue, with its dedicated binary star solutions and its improved proper motions, will either confirm or deny the closest flyby scenarios for HD 7977. It will refine the trajectory of Gliese 710. It will identify new encounters that we have not yet discovered, and with each new discovery, our understanding of the solar system's history will deepen, and our appreciation of its fragility will grow. There is a philosophical dimension to this story that is worth acknowledging explicitly. For most of human intellectual history, we have tended to think of our place in the universe in one of two ways. Either we are the center of creation, the purpose around which the cosmos was organized, or we are utterly insignificant, random accidents in a universe that neither knows nor cares that we exist. The story of HD 7977 suggests a third possibility, that we are connected, not central, not insignificant, but woven into the fabric of galactic processes in ways that are both meaningful and humbling. Our planet's history is not self-contained. It is part of a larger narrative that includes the motion of stars through the galaxy, the gravitational dynamics of the Oort Cloud, and the slow, patient work of gravity across timescales that dwarf anything in human experience. We did not choose to be part of this narrative. We did not earn our place in it, but we are in it, and our ability to recognize that fact, to trace the trajectory of a star that passed by millions of years ago, and to understand what its passage meant, is itself remarkable. It is perhaps the single most extraordinary thing that has happened in the solar system since it formed. Not the star's passage itself, which was a routine gravitational event of the kind that occurs throughout the galaxy every day, but the fact that on one small planet, a species arose that could look backward through time and understand it. There is a kind of grace in that understanding. It does not protect us from the next stellar flyby. It does not deflect the next comet, but it places us in the cosmic story. It gives us context. And context, in the face of the universe's vast indifference, is not nothing. It is perhaps everything. It is the beginning of responsibility. What makes this story particularly relevant to our present moment is the convergence of several lines of evidence. The Gaia mission continues to refine its stellar catalogue with each data release, and the final catalogue, expected in the late 2020s, will include dedicated solutions for binary and multiple star systems that should resolve the "are we" ambiguity surrounding HD 7977. The Vera C. Rubin Observatory, currently under construction in Chile, is expected to begin its 10-year legacy survey of space and time in the mid-2020s, which will discover thousands of new trans-Neptunian objects and potentially identify orbital signatures consistent with past stellar flybys. And theoretical work on the Oort Cloud continues to advance, with increasingly sophisticated simulations that model the coupled effects of stellar encounters, galactic tides, and planetary perturbations over the full age of the solar system. We are approaching a moment when the story of HD 7977 can be told with far greater confidence. Within a decade, we may know whether this star is truly a single body or a binary, what its exact closest approach distance was, how it affected the orbital distribution of the outer solar system, and whether its passage correlates with any observable features in the geological record. The mystery will not be fully resolved, because some aspects of it are inherently uncertain. But the broad outlines will be clearer, and those outlines will tell us something not just about one star's passage through our neighborhood, but about the fundamental vulnerability of planetary systems embedded in a dynamic galaxy. But understanding does not confer protection. We can catalogue every star that will pass near the solar system in the next 10 million years. We can model the resulting comet showers. We can estimate the impact probabilities. But we cannot stop them. We cannot redirect the stars. We can only know what is coming and prepare, in whatever modest way we can, for its consequences. In the end, the story of HD 7977 is a story about knowledge and humility. The knowledge that our solar system is embedded in a dynamic, evolving galaxy, and the humility to accept that some of the forces shaping our world are entirely beyond our control. 2.5 million years ago, a star passed through the darkness at the edge of our solar system. It was roughly the same size and temperature as the Sun. It was a G-type main sequence star, an ordinary yellow dwarf, the most common variety of hydrogen-fusing star in the galaxy. If you could have stood on a planet orbiting that star, our Sun would have appeared as just another bright point of light in the night sky, unremarkable among the billions that fill the Milky Way. And if you could have watched from the Oort Cloud as the intruder drifted past, you would have seen nothing dramatic. No collision, no explosion, no flash of light, no sound, of course, because space carries no sound. Just one star slowly, silently crossing the sky of another, 2 points of gravity passing in the cosmic night. But something did happen. Gravity reached across the void. It reached across thousands of astronomical units of empty space, distances so vast that light itself needs hours to cross them, and it touched trillions of frozen bodies that had been drifting in their orbits for billions of years. Most of them barely noticed. Their orbits shifted by imperceptible amounts, fractions of a meter per second, changes so small that they would not become apparent for millions of years. But some were pushed harder, some were nudged inward. Their orbits tightened, their perihelia shortened. Their long, looping paths through the outer darkness were compressed, reshaped, redirected. They began the long, slow fall toward the Sun. It would take hundreds of thousands of years for the first of these displaced objects to arrive in the inner solar system. They would come one at a time, separated by centuries or millennia, bright streaks across the night sky, tails of gas and dust streaming behind them, as the Sun's heat vaporized their ancient ices. By the time the shower peaked, the star that had caused it was already millions of astronomical units away, receding into the galaxy at tens of kilometers per second, oblivious to the consequences it had left behind. No one on Earth noticed the shower, if indeed it came. There was no one to notice, The planet was populated by creatures that had no capacity for astronomy, no written language, no conception of the sky as anything other than a roof. The hominids that walked the plains of East Africa during the Pliocene-Pleistocene transition, the beings who would eventually give rise to our species, looked up at the night sky and saw lights. They did not see trajectories, orbital parameters, or gravitational perturbations. They did not know that a star had visited their solar system. They did not know that the changing climate, the spreading ice, the shifting ecosystems around them might have been influenced, however subtly, by an event that had occurred in the outer reaches of a cometary cloud they could not have imagined. We know this now. We know it because we built satellites that measure the positions of stars to fractions of a milliarc second. We know it because we developed mathematical tools that can trace a star's trajectory across millions of years of galactic drift. We know it because we constructed computational models of the Oort Cloud and ran them forward and backward through time to see what happens when a star passes through. For the first time in the 4.5 billion year history of this solar system, there exists a species on one of its planets that can look in the past, identify the intruders that came and went in silence, and begin to understand what they did. HD 7977 is gone now. It sits 247 light-years away in the constellation Cassiopeia, an ordinary star among billions. It carries no physical sign of its ancient passage through the solar system. Stars do not scar, they do not accumulate marks from the places they have been. It does not remember us. It does not know that its gravity may have sent a shower of icy bodies cascading toward a small blue planet where, 2.5 million years later, a species would arise that could trace the encounter backward through deep time and give the intruder a name. And Gliese 710 is still coming. 1.3 million years from now, give or take a few tens of thousands of years, it will enter the Oort Cloud. It will drift through the outer reaches first, barely noticed by the frozen sentinels that populate that region. Then it will penetrate deeper into the denser inner cloud, where trillions of objects orbit in near-perfect stillness. At its closest, roughly 10,600 astronomical units from the Sun, it will be close enough to significantly perturb the orbits of millions of cometary nuclei. Some will be flung outward into interstellar space. Others will fall inward, beginning the long spiral toward the inner solar system. The resulting shower will last millions of years, producing perhaps 10 naked-eye comets per year at its peak, transforming the night sky into something alien and spectacular. Whether anyone will be here to see it is a question that depends on factors far more immediate and terrestrial than stellar flybys. And beyond Gliese 710, there will be others, stars we have not yet identified, stars whose Gaia measurements have not yet been processed, whose trajectories have not yet been calculated, whose future encounters with our solar system remain hidden in the vast, still-growing database of galactic astrometry. Some of these will be distant and harmless. Some may come closer than anything we have yet recorded. We simply do not know. The universe is full of objects in motion. Stars orbit the galactic center. Galaxies orbit each other in clusters and superclusters. Clusters merge, dissolve, and reform over billions of years. There is no stillness anywhere, no absolute rest, no fixed point around which everything else revolves. Motion is the fundamental condition of existence. From the orbiting of electrons around atomic nuclei to the recession of galaxy clusters toward the edge of the observable universe. And in a cosmos defined by motion, encounters are inevitable. Every star in the galaxy has been passed by other stars. Every solar system has felt the gravitational tug of an intruder. Every Oort cloud around every sun-like star in the Milky Way has been stirred by the passage of neighboring suns. What happened to our solar system 2.5 million years ago has happened to countless other systems across the galaxy. It is happening right now, somewhere in the spiral arms of the Milky Way, as a star drifts through the cometary cloud of another, sending icy bodies cascading toward planets we will never observe. It is a universal process, as common and as unremarkable as the drifting of clouds across a summer sky. But it is not unremarkable to us, because we are here, because we evolved on one of those small planets, around one of those ordinary stars, inside one of those fragile cometary clouds. Because the comets that the Oort Cloud sends inward helped deliver the water in which the first cells divided, the first organisms breathed, the first eyes opened, and because those same comets, arriving in excess, can erase everything we have built and everything we are in a single, searing moment of kinetic energy converted to heat and light and destruction. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. We emerged on a world that was shaped by forces operating on scales we can barely comprehend, forces that stretch across light years and unfold over millions of years. The star that passed through our solar system 2.5 million years ago did not know we were coming. And we standing here now, tracing its path through the Gaia data on our computer screens, do not know what is coming next. The solar system is quiet tonight. The Oort Cloud drifts in the darkness, its trillions of frozen inhabitants completing their million-year orbits in silence. The planets trace their ancient paths. The sun shines, as it has for 4.5 billion years, warming the thin skin of atmosphere and water that we call home. The stars wheel overhead in patterns that our ancestors named after gods and animals and heroes, patterns that shift so slowly that 10,000 human generations have passed without noticing the change. But somewhere out there, beyond the reach of our best telescopes, beyond the edge of our charts, a star is moving. It is drifting along its own path through the galaxy, pulled by the same gravity that holds us in our orbit, and its trajectory is slowly, imperceptibly, bending toward our neighborhood. It may come close, it may not. It may pass through the Oort Cloud and stir the ancient ice. It may sail harmlessly past at a distance of many light years, a cosmic ship passing in the night. We will not know until we measure it, catalogue it, trace its path across the decades and centuries to come. And when we do, we will add it to the list, alongside HD 7977 and Schultz's star and Gliese 710 and all the others we have found and all the others we have yet to discover. Another entry in the long-growing catalogue of visitors who have passed through, or will pass through, the fragile shell of ice and silence that surrounds our home. The Oort Cloud does not care about our plans. The galaxy does not know our names. The stars move according to gravity, not intention, and their paths are indifferent to the civilizations that may exist in their wake. A star came. A star passed. A cloud was stirred. Comets fell. A world changed. A species arose. And now that species looks up at the sky and wonders what else is out there, drifting toward us through the dark. That is the story of HD 7977, a quiet star, a silent passage, and consequences that echoed across 2.5 million years, shaping the world that would one day produce the minds capable of understanding what had happened. The sky is dark, the stars are moving, and the Oort Cloud waits,